Okay. Now, one last aspect on this trigonometry that I want to discuss, which we require in as part of calculus and other computations, is the variation of sin theta and cos theta. That is how they vary when you increase theta. No? So, the rate of variation that we need to see. And one of the simplest examples is if you have two angles, A and B, and what happens to sin A when you add B to it, that is sin of A plus B. Supposing we want to find sin of A plus B and cos of A plus B, that is the foundation which is required. One of the foundations which is required, there is one more foundation which we will discuss next after we become familiar with limits. These two are necessary to start our discussion on calculus. Okay. So now we want to look at, supposing I have two angles, A and B, what is the value of sin of A plus B and cos of A plus B, correct? So let us just look at that. Let me draw one simple diagram. As part of this discussion, let us make an assumption that we have the two angles A and B, both are less than 90 degrees. And the total also is less than 90 degrees. Otherwise, when the total becomes more than 90 degrees, our geometric construction will not be proper. But then that also will be correct. Correct because our algebraic signs plus and minus, that will work out all right, but then I don't want to worry about that right now. You can always do that as an exercise. When A is greater than 90 or B is greater than 90 or A plus B, A and B may be less than 90, but combined together it may become greater than 90. Remember, these are the two angles. When you add the two angles, it may go past that y-axis. No, it's quite possible, and that I want you people to look at it as a separate exercise. So I want to only look at the case here where A and B, A plus B is less than 90 basically. Now we are interested in the trigonometric functions of A plus B as an angle, right? And when you want to do that, obviously you need a Pythagoras or you need a right angle triangle to find sin of A plus B and cos of A plus B. You need to drop a perpendicular. So that is the minimum construction. So let us just do that to start with. We will also need the trigonometric functions of A as well as B also, because that is what we want to find out as an end result. So we will also drop a perpendicular to this side line from the top and another perpendicular back to the original line. I am constructing enough number of right angles here basically, so that we can look at trigonometric functions of A, I've got a right angle triangle. Trigonometric functions of B, I've got a right angle triangle. Opposite side, hypotenuse, all that is available. And for A plus B also, I've got a right angle triangle. So basically, I've got all the three right angle triangles here. It should be easy to figure out how sin A plus B can be computed in terms of trigonometric functions of individual A and B. Correct? That's right. Now, if you look at sin of A plus B to start with, you find that is the opposite side by hypotenuse, correct? Now, our opposite side is equal to hypotenuse multiplied by sine of b, sine of a plus b. That also you can think of it like that. So, this hypotenuse anyway, because of Thales' theorem, it doesn't matter how long that is, from which point we start drawing the perpendiculars, actually it makes no difference because we are only looking at ratios of the sides. I can, without loss of generality, assume that the hypotenuse is 1. Just assume it is 1 unit, yeah, doesn't matter. That makes life simpler, simpler. For example, now the opposite side, I have to keep showing you the actual side here. Instead of that, if I write some names for the vertices, I can specify them with names also. So let's just call this, since I have used A and B already for angles, I'll start with the B, correct? Yeah, I've already used A and B as angles, so let's start these vertices names as maybe C, I got a D, E, F, and a G. Correct? I'll do one small construction because we need to be able to figure out the length FD, whereas we know GE only. So I need to draw one perpendicular from G to this. Basically completing this rectangle, no? So, and we can call that point as H. Now, let's come back to our original thought. I have assumed the hypotenuse CF as one unit, which means the opposite side FG must be equal to sine B. I can write the value there straight away. Correct, no? Opposite side is equal to hypotenuse multiplied by sine of the angle. Hypotenuse is 1, so that value is sine B itself. Similarly, this, what is CG? CG will be cos B, because that is the adjacent side for this angle B, hypotenuse is 1. So that will be cos B, correct? Now, coming to the other triangle here, CG, I got the angle A and I got a hypotenuse. Now it is not 1, it is cos B. Therefore, what is the opposite side? Hypotenuse multiplied by opposite side, which is sin A cos B. Right? Sin A, sin multiplied by hypotenuse is the opposite side. Similarly, what will be this distance C to E? Will be hypotenuse multiplied by cosine. So, which will be cos A cos B. Right? Now, I have one more right angle triangle here, which is FHG, which has a hypotenuse, but angle is not anywhere. No? So, we have a problem with the angle. That also we can figure out because of alternate angles, and we have parallel lines. Everywhere we have parallel lines. Now you see angle A, if you look at the angle A here, angle A is between, and I've got a parallel line here, HG for the angle A. Therefore, the alternate angle, that is a Z, no? You got a Z there. Therefore, that angle must be angle A only. No questions on that. Right? Then, now we had dropped a perpendicular FG to the line CG. Therefore, this thing is a right angle and A is part of that right angle. So, the balance angle must be complement of A. 90 minus A will be this angle, right? And we also have another right angle triangle FHG, where these two angles, non-right angles, add up to 90 degrees. Therefore, the angle at the top is a complement of this angle. It's also a complement of A, which means that the top angle must be A. That's the same as A. Because from here, in fact, that is also natural. You see, original angle A was between these two lines, right? Now, I have got perpendicular to this line and a perpendicular to this line. So, the two perpendiculars will form the same angle, no? Because of alternate angles, then corresponding angles and so on. So, they'll form the same angle. Therefore, that is also A. Which means now I can write the values for AH and HG in terms of the hypotenuse because I know the angle. So, what is the value of AH? You can write it down. What is AH? AH is adjacent side. So, that means hypotenuse multiplied by cosine of the angle. No? So, it is cos A sin B. HG is opposite side of this A, hypotenuse is sin B, so it will be sin A sin B. Correct? So now I have got all the pieces, rectangular pieces we have got, we just have to write the answer now. So what is sin of A plus B? Now we can write that. It should be, I don't need to prove anything, I just have to write the answer. What is sin of A plus B? Is the opposite side by hypotenuse. This entire thing, hypotenuse is 1. I just need FD actually. FD is what I want. And FD is FH plus HD. If you want, we'll write that expansion. So, is equal to FD, which is FH plus HD. I will write that as HD plus FH. HD plus FH. And what is HD? It is the same as GE, no? Is sin A cos B. And what is FH? Cos A sin B. That's the answer. Already got the answer. No? Sin of A plus B, sin A cos B plus cos A sin B. Straight with one simple construction. And having drawn enough number of perpendiculars to calculate the trigonometric functions. Any trigonometric function will always require a perpendicular. So you get one adjacent side and you get one opposite side. Adjacent side will give you cosine, opposite side will give you sine. So now what is cos of A plus B? Is adjacent side divided by hypotenuse. What is the adjacent side of this? Is CD. Correct? Hypotenuse is still 1. For A plus B, CD is adjacent side, hypotenuse is 1 equal to. Now, how do you express this CD in terms of the known values? Is CE minus DE. Right. And what is CE itself? We already got value. Cos A cos B. Minus, what is DE? Same as HG. And I got a value already. Minus sin A sin B. So cos of A plus B is cos A cos B minus sin A sin B. Sin of A plus B, sin A cos B plus cos A sin B. And one more fundamental property of these trigonometric functions is the Pythagoras theorem itself. Take sin A and sin B, for example, right? Sin A and sin B, and you square them up and add. So what is sin squared A plus cos squared A? Sin squared A is sin A whole square plus cos A whole square. Sin squared A plus cos squared A will be sin A is the opposite side, cos A is the adjacent side. The squares on the opposite side and adjacent side, if you add, you will get the square of the hypotenuse. And that hypotenuse is 1. So, sin squared A plus cos squared A is always 1. The sum of sin squared and cos squared of any angle is always going to be 1. So this is another identity for sines and cosines that we have to remember, and that these formulae are required to derive, to do calculations, computations on trigonometric functions. We'll need that. So that covers that ground. Okay. So now we can start looking at the convergence of the series. This is enough background. I will not specifically introduce tangent function, tan, secant, cosecant. I will not bother doing that. Okay. So let us go back to the earlier series that we derived in the last session. Last week, we got a function fx, which is basically the compounded interest, indefinitely compounded with the least period of time. What is the total interest and the capital that we get at the end of a period, you know. That we can start with that. Okay. You can do an exercise where a plus b is greater than 90 degrees, and when you drop the altitudes and perpendiculars, instead of this plus sign, you might probably get a minus sign, and but there the sine and cosine themselves may be plus and minus. So in combination, it will work out, and you will get the same identity for sine a plus b and cos of a plus b. So now we were looking at the function f of x. F of x is a function which is really the total amount that you get at the end of 1 year. If you have 100x% interest compounded indefinitely with 0 time, you know. So basically that's what you get. We had derived that as 1 plus x divided by 1 factorial plus x square divided by 2 factorial plus etc. till infinity actually. And this can be also written as a sigma function. Sigma is add all the items, conditions I will write here, of x power n divided by n factorial. And what is, first one is 1 itself. So we start with n equal to 0. What is x power 0 is 1, of course, no problem. And 0 factorial actually doesn't exist. So we'll assume that 0 factorial is 1. Just make an assumption. 1 factorial is 1, 0 factorial also is 1. In which case that will be that will be the first term, second term, everything is correct. From n equal to 0 to infinity. When you add, so there is sigma n equal to 0 to infinity of x to the power of n by n factorial. If you add, what you get is the value. Now, depending on the x, that value will be different. So I've just called it function of x. You know, so depending on x, whatever the value of x you use, you get a different value. And we also solved one other. We did a long multiplication to prove that f of x, if you multiplied by f of y, that means 2 different values, what you get would be f of x plus y. In fact, this identity itself is a definition for one class of functions which are called exponential functions. They are called exponential functions. Exponential functions of a variable is when you multiply the values for 2 different values, what you get is the value of the function for the sum of those 2 values, x plus y. And when I say x plus y, I have not said whether x is positive, x is negative, or whether x is rational, x is integer, not integer. We have not even discussed all those aspects. We can start looking at those aspects, you know, to start with. So what is the first thing that we do is, what is f of 0? That means x value is 0. When x value is 0, each of these terms, x by 1, x squared by 2 factorial, x, everything goes to 0. Everything is 0 except that first term, which is 1. So f of 0 will be equal to just 1 itself. Simply 1. No questions on that. Next value we want to look at is f of 1. We'll set the value as 1. That means 100% interest. 100% interest, if you do, what is the result that we get? We are going to get f of 1 will be 1 plus 1 over 1 factorial plus 1 over 2 factorial plus etc. till infinity. Correct now? So now we have still not proved that this infinite series is what we call convergent. So when you have an infinite series, any infinite series, the basic question you must ask first before you do anything with the series is whether it is convergent or it is divergent. Convergent means it converges to a finite value. So it's got a limit there. No? So that means you can assume that value is correct. That limit value is correct. Even though I can't write it down, it will be an irrational number, definitely. In fact, it is actually a transcendental number. All these infinite series, what they add up to are called transcendental numbers because they cannot be roots of any finite polynomial equations. So they are transcendental numbers, which means actually basically another way of looking at the same thing is they have an infinite number of non-repeating decimal digits. If you want to look at it, if you look at that real number system itself, these real numbers we constructed using the Euclidean plane, one line, and said any point on that will be one real number. No, that is the construction that I did for real numbers. There is actually another construction for real number which is based on our decimal representation. Positional decimal number. Decimal representation itself can be used to construct real numbers. What is a most general decimal number that you can write is I can have some n number of digits, maybe k number of digits, bk minus 1, etc. all the way till b0 dot, there is a decimal point. So these are integral digits, bk minus 1 all the way till, so I got k plus 1. If you stop at b1, then it will be k, a number of full digits, then followed by a1, a2, a3, etc. to any number of digits that you can write. And in fact, we can assume infinite number of digits here. Even natural numbers also can have infinite number of digits. What is 1? Is 1.000, keep writing 0. Right, infinite number of zeros followed by a 1 dot is actually natural number 1. So even integers can be represented as infinite number of digits, and that 0 repeats itself, right? Quite possible. Or you may have, if you don't have repeating digits, I have 1.23, you can always write that as 23 followed by 0, 0, 0, 0. You can always write trailing zeros in a decimal number, which means we can always look at decimal representation as an infinite number of digits. No loss of generality. So what we are saying is that any decimal number that you write with infinite number of digits on either side of the dot, doesn't matter. Left side also you may want to write infinite number of digits if you want, no problems. That represents a real number. That's the construction for real numbers using decimal representation. Now this throws up quite a few interesting properties of this decimal number, infinite decimal number. That's the reason I took up that. This is a known, what I've written so far is already known, no? But I would like to look at a couple of these examples of the so-called infinite number of digits to show you there's some peculiarities there which you might find illuminating. No? We'll take one example. For example, I write 0.333333 indefinitely. That means it's not 0 which is repeating. I got a 3 which repeats indefinitely. No? So now this is definitely this is a real number, no questions, because that is our construction. And what is that real value itself? I don't know what is that value. Supposing I don't know what is that value, very easy to figure that out. Supposing x is that value. I'll assume x is a real number whose representation is 0.33333 indefinitely. Infinite number of, infinite means unrestricted. Any number of 3s. You want, we already have 1,000,000 3s. You want more? I'll give you more. I got any number of 3s that I want. I can put there, right? How do you do that? All you do is just multiply that by 10. 10x. What is 10x? 10x is simple in decimal positional number is to move the decimal point to the right by one place. No, we know how to do that multiplication. Will be 3.333. Actually speaking, we are supposed to have 1 less 3 here after the dot when compared to the previous, right? But then because it is infinite number, what is 1 less than infinity? Infinity only. It is always same. So we can assume these two, this 0.333 and this 0.333. In fact, we had the old Sanskrit statement itself in Vedas. 3,000 years ago, our Hindu rishis had discovered this infinity is represented as a number which is called Purnam. Purnam. Purnam is complete. Purna is complete. Everything else is half complete. Infinity is complete. So it is called Purnam. So they said, there is one short poem, or not even a poem, one small line, which says, Purnasya Purnamadaya Purnamevavashishyate. That means subtract Purna from Purna. What are you left with? Purna only. Don't think anything is going away because it is complete. From the complete, if you take something out, you are still left with complete. That is the meaning of that statement. So we can assume, safely assume, that the number of 3's beyond this dot is the same in both of these cases. Now you do a subtraction. Simple. Just subtract. So what is 9x equal to? Subtract the first one from the second one. We get a 3 here, and all the rest will go to 0 because you got infinite number of 3's will get cancelled with infinite number of 3's. So I will be left with 3. So what is the value of x? 1 by 3. In fact, if you divide 1 by 3 into decimal representation, start dividing, what you get is 0.333333. It keeps going now. There is no limit to that. It keeps going. This is exactly what it is. It's a rational number. Now you can see, even though you got infinite number of digits, it's a real number, and also it is rational because it is a fraction, right? So the reasoning is very simple. Whenever a set of digits, block of digits, not just one, it could be multiple also. In fact, you can write on your own, you can write a couple of examples of repetition. For example, you can try this out. Supposing you have a number which is 0.12121212. That means that block 1, 2 I am repeating, blocks. Repeating blocks at the end actually. Initially I can have anything. I can have 0.987, any number of digits you can have. What we are worried about is the trailing end of this infinite number of digits is a series of same block of digits repeating. Actually becomes a rational number. You can just calculate what is the value of this. You can figure out by simple multiplication. In this case, you will have to probably multiply by 100, I think. Just figure out, as an example, you can figure out, multiply by 100 and subtract. So it will be a fraction of 99. So you will get that. So 99 would be the denominator for that rational fraction. So whenever you have block of repeating digits, it becomes rational. Obviously, if there is no block of repeating decimal digits, it is not rational. It is only real. It is irrational. Pi is one example. Pi is got 3.14 something, right? So now that keeps going, and there is no repetition there, right? Square root 2 is the same, 3.142 something, and there is no repetition of digits there. So when there is no repetition of decimal digits, it is always irrational. Whereas when there is a repetition, any kind of repetition, what you are going to get is a rational number. But then this infinite number of decimal digits itself can be used as a construction for rational numbers. Just like we use the line, points on a line to construct the real numbers. And now in fact, each of these numbers, whatever you construct, can always represent as a point on the real line. It will become one distinct point which is different from other points. That's why that real line is very dense actually. Between any 2 points, any 2 distinct points, however close they are, you can find infinite number of other points. Again, between each of those infinite number of points, you will find infinite number of other points. So you can imagine, it is so dense, filled with points, right? So when you write a interval, for example, a to b, 1, 2, how many numbers are there? Infinite number of numbers. Any number of numbers that you want, inside that, a real number. So you have to keep that picture in your mind. That means close to 2, how many you can find? You can find infinite number of points. However close to 2 you get, you will still have infinite number of points on that line, or in the decimal case also. In fact, that fact we are going to use to look at this convergence and divergence of infinite series. Now, what is convergent? Like I said, convergent really means finally it has got some limit here. It is not going like 1 by that 0.333 is a convergent series of decimal digits. Value is actually not 1 by 3. Really speaking, we wrote it as 1 by 3, but actually it is not 1 by 3 unless you write actually infinite number of dot 3's, no 333, which you can't write anyway. Infinity is not there. But then we say it is 1 by 3. We'll say the limit is 1 by 3 because we can always make it as close to 1 by 3 as we want. However much close you want, I can go to 1 by 3. So that is known as a limit, and we write that itself as a value. So we'll write 0.33333 as 1 by 3, even though it's not really equal to that value. No? Now, so convergent means it is there is a limit, which is a finite limit. That is the meaning of this. It's got a finite limit. Is the meaning of convergent. We will not reach that limit. Probably we will not reach the limit, but we can get as close to that limit as we want. However close we want, we can reach there. So we'll call that itself as a value, as a limit. Then divergent means obviously no limit. Divergent goes to either plus infinity or goes to minus infinity. The two cases of divergence is plus infinity or minus infinity. In fact, there is a third type of total for the infinite series also, which is called oscillating. That means it doesn't go to infinity. It's not divergent. Divergent is like this. No? Convergent is like this. No? Convergent is converges to a point. No? Divergent is going away from point. No? Diverges. No, this is neither convergent nor divergent. No? Is oscillating. I'll give a simple example of oscillating. Is sin x as x tends to infinity. What is the value of sin x? Remember, sin x will always have value between -1 and play. It oscillates between -1 and +1. No? So it's not convergent. It's not divergent also. So it is oscillating. So that is a example of oscillating. Now we have enough background now to sit down and discuss whether this function I originally wrote was convergent, not convergent. How do we prove that it is convergent? I mean, how do you prove, given as infinite series, how to prove whether it is convergent or divergent or oscillating? So we look at that. So let us look at that, how to find out. And that brings up some very interesting philosophical questions also. Let me discuss that first before we actually get into the nitty-gritty of deriving whether this is convergent, whether it is not convergent. Or we can start with one simple example of a convergent series. And many times people have used geometry itself to find the convergence, no? to figure out whether it is converging, not converging. I'll give a very simple example for convergence using geometry. Supposing there is a point, one person or object or whoever is standing, and he wants to walk across to another point. Right? Point A to point B. That is the intention. Very simple. Now, this is like a race, between rabbit and, you remember, tortoise. It's like a tortoise, actually. The fellow says distance is too far. It will be so far. I can't do that. What I will do is I will visualize the distance, close my eyes and say I will walk half the distance. So that is what he's going to do. So what is the tortoise doing? To the midpoint. So first walk is up to the midpoint. Half. Then it opens its eyes and looks at it. Oh, I still need to go some distance. No? Obviously there is, when you say I walked only up to half the distance, there is some more distance left, right? So it does the same thing again, recursively. He says, oh, I need to go this distance. I'll close my eyes and walk half the distance again, half only. So that means it goes up to this point, correct? No? Next, again opens the eyes and says, I want to go till there. But I will close my eyes, go halfway, always halfway. No? Again halfway, right? Now, this tortoise, you see, it will never cross B. We agree on that. Because always going towards B only and less distance on what is already there. And it will never reach B also. Because there is always a distance. When you travel only half the distance, there is always going to be some distance left. So it never reaches B, never crosses B, right? Understand? So in fact, it takes infinite number of attempts to actually reach, not even reach. But it's got a limit, that limit is B itself. No? So what is the total? What are we doing here? Actually, we got an infinite series here. First distance is, assume the total distance is 1 unit, 1 mile, 1 kilometer, 1 meter, whatever it is. So the first distance tortoise travelled was half. Next distance it travelled was half of that half, right? So it will be 1/4. Next will be 1/8. Next will be 1/16 and so on, right? So keep adding this. What you get is a geometric progression. Actually, what you have is a geometric progression. You can keep adding endlessly. And finally, what is the answer that you will get? Is 1. 1 is the answer. Not quite. It won't reach 1. But this total can reach as near 1 as you want by taking sufficient number of, adding sufficient number of terms. So this geometric series is actually convergent. And we say it converges to 1. Right? And we can prove that also very easily. Geometric series, convergence, we'll do that next. How do we prove that? Supposing what we do is we write that as a function actually, first to start with. So I'll say there is a function called S which depends on a number called N. N is a natural number. That is, I want to add or find out what are called partial sums. This is the total sum. Total sum is still infinity. I want to do only a partial sum. That means some n number of terms only I want to add is known as a partial sum. What is the partial sum for Sn? Sn in this case, when you say I want to add, is half plus half squared plus half cubed, etc. half to the power of n minus 1. Correct? That is a n term. N terms I have added, partial terms, correct now? Sn. Now, how do you find this value? Just like we did for decimal digits. Actually, procedure is very simple. Multiply by half. So, what is Sn? Half Sn will be, the half becomes half squared now because I have multiplied by half. So, this becomes half squared. Half squared becomes half cubed. Cube becomes to the power of 4 plus etc. Half to the power of n minus 1 becomes, actually there is a value which is half to the power of n minus 1 also behind this, no? There was a n minus 2 there, so I will write that. Half to the power of n minus 1 for that n minus 2, and for this plus half to the power of n, correct now? One additional term. So I got 1/2 here which is outside, 1/2 to the power of n which is outside. Other than that, you will find every other power of half is matching. Correct? No? You understand? Therefore, we do a subtraction. So what is Sn multiplied by 1 minus half? Subtract the second one from the first one. All these will go to 0. All these terms, till in any number of things that you have. So the first half is not cancelled. So is equal to half minus the last one also is not cancelled, half to the power of n. Correct? Now this partial sum Sn, or you can take this to the other side. Therefore Sn is equal to 1 minus half is half. So that means that 2 will get multiplied on the other side, will be 1 minus 2 times or 1 time, 1 by 2 power n minus 1. Correct? So now as n keeps increasing, this one remains the same of course, and this 2 power n minus 1 keeps increasing, and 1 over 2 power n minus 1 keeps decreasing towards 0. So when n tends to infinity, we say this 1 over 2 power n minus 1 tends to 0. Therefore, Sn will be equal to 1. That's the limit. So geometric series is you have to say that is convergent in a reserved manner, because instead of having powers of half, if I had powers of 2, what would happen? That means if I had 2 plus 2 squared plus 2 power 4, 2 power 3 plus 2 power 4, etc. Is that convergent or not convergent? Definitely not convergent, because this goes to infinity. No, each term itself goes to infinity. So total of so many infinities is still infinity only, obviously. So this is a divergent series. So geometric series converges on only one condition, that the successive terms keep decreasing. Successive terms have to be decreasing, means the ratio has to be less than 1. Ratio of successive terms. If you call this, I got a term which is the nth term, we'll call it Tn. And I got a next term which is Tn plus 1. And what is the value of Tn plus 1 divided by Tn is a question. That has to be less than 1. Otherwise, it will be divergent. So geometric series converge, this is called, this is the ratio. Ratio of consecutive terms. If it is less than 1, then the geometric series is convergent. If it is greater than 1, then it is divergent. And if it is equal to 1, it is divergent, because we are adding, no? We add infinite number of something, whatever small number, so it will become divergent. So only when it is strictly less than 1, we have this convergence property, correct? Now, this brings us one other series, which is a harmonic series. Geometric series is not very interesting because it goes to convergence so fast. You understand? See, in this case, when somebody says, so let's put that same statement in words, no? When somebody says, I've got a geometric series, in general I can write as a plus ar plus ar squared plus etc. till infinity, no? So this is a geometric series. Now, how do you know it's convergent or not convergent? We need to examine it, no? So we need to conduct an examination, conduct a test. Test or examination. So what we have, this is one geometric series, but I got our own fx, 1 plus x by 1 factorial x squared by 2 factorial. I got our own function also. That means actually there are the infinite number of infinite series which are there. No? There are all the candidates. Now I want to find out convergence. I have to run a test on all of these candidates. No? So we have to give an exam. Running a test is, you have to give an exam to those fellows, right? So when you conduct the test, some of the series will fail, we'll say diverges. Some series will succeed, test is success. So then it is convergent. No? So in this case, what was the test? Our test is very simple. Check the ratio of adjacent terms. Right? In this case, it is R. That R, and check whether that is greater than 1 or less than 1. Less than or equal to 1. So we are saying our test is very simple. When you are given a geometric series, find the ratio of adjacent terms. Since it is geometric series, the ratio is fixed for any pair of adjacent numbers. And if that, I think I made a mistake, it should be less than 1 or greater than or equal to 1. If that ratio is greater than or equal to 1, it is divergent. If the ratio is less than 1, it is convergent. It's a simple test, right? Simple test. Now, we come to the next series. This test was very simple, so very easy to conduct also, right? And in fact, there is one even more elementary test we have to conduct before we even come here, to conduct this. This is a simple test. There is even a simpler test is, if a series has to be convergent, an individual term has to go to 0 only, You understand? So that means it has to be, that is, a term must go to 0. Otherwise, if a term doesn't go to 0, as n goes to infinity, there is no question of convergence. No, obviously you will be adding infinite number of non-zero items, it will be divergent. So obviously it is going to become divergent or oscillating, as the case may be. Definitely is not convergent. Our interest is only in convergence. So a term must go to 0. That is a condition. In fact, when you had a ratio which is bigger than 1, you saw the term doesn't go to 0. Whereas only when the ratio is less than 1, actually the term goes to 0. No, that is why we could pass this. We can pass this series as convergent. No? Convergence test. There is a pass and there is a failure. Correct? No? We could do both. And this is the fundamental requirement. Now we'll write the next series, which is called harmonic series. Now why it should be called harmonic series also I will tell you. These came up in music actually. Harmonics are a set of frequencies for a bass frequency. They are actually called harmonics. So when you say I got one fundamental frequency at which I am singing or playing an instrument, half that frequency is a harmonic, 1/3 that frequency is also a harmonic, 1/4 that frequency is also a harmonic, and so on. So every fraction of that frequency is a harmonic. Reason is simple. When you say I got a frequency of waves, this F, so I got a wave which is going like this. No? Now if you got half the frequency, which means, how will you write that? Every two of this fundamental frequency, it will come and touch it. So there is a coinciding point. For the ears, it is very pleasing to listen to those frequencies. That's why they are known as harmonics. So this harmonics, basic harmonic series I have already written there. So let's just write the infinite series for harmonics. Is the total of these numbers, which is 1 plus half plus 1/3 plus 1/4, etc. till infinity. It passes our fundamental test, what we call the fundamental test. Individual term goes to 0. 1 over n, as n becomes indefinitely large, goes to 0. That condition is satisfied. Fundamental test is satisfied. Now if you take the ratio of two consecutive terms, it's not a geometric series, but anyway the ratio is always less than 1. You can see that every succeeding term is less than the previous term. 1/5 is less than 1/4. 1/6 is less than 1/5. 1/7 is less than 1/6, and so on, right? And as you add more number of terms, the value of the total keeps increasing, right? So it is known as a monotonically increasing sequence. Monotonically increasing. Monotonically means in the same direction. That means it doesn't increase and decrease. Total will only keep increasing. No? The total of items will only keep increasing. But then each time we add a new number, that new number keeps decreasing. That is a different issue. So now the question comes, will this converge or does not converge? In the face of it, you can't test, you can't say. It becomes smaller and smaller. Now will it reach will it be convergent? Yes or no is the question. Now that first time in the 14th century or 13th century, our friend, I wrote his name in the morning, Nicole Osserme, French name. He is the first person to have stated that this harmonic series is divergent actually. It's not convergent, it is divergent. How did he prove that? Very simple method. I'll show you that also. Extremely simple method is we write the same harmonic series and we group the terms in a particular way that I am going to show you. So we write first one, we write the half. No problem. So that means I have written now one term here. This one you can ignore if you don't want. So one term I have written first. Next two terms I will group together. 1 by 3 by 1 by 4, I will call that as one group. I followed that up by 1 by 5, 1 by 6, 1 by 7, 1 by 8, 4 numbers. Following 4 numbers, that means what I am doing here is 2 power 0 numbers I write as a group, that is 1. Then 2 power 1 numbers I have written as a next group. 2 power 2 numbers I have written as a third group. And the fourth group that I am going to have is, I will not bother writing it, starting from 1 by 9 up to all the way till 1 by 16 will be 2 power 3 numbers that I want to group together. The last of those will be plus 1 by 16, correct? You understand? In fact, you will see that the geometric progression that we had, 1 by 2, 1 by 4, 1 by 8, 1 by 16, they will be the last members of each one of those groups. That's how I have grouped them. Right? Now, if you take any one group, for example, take this, 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8, we know that each term, successive term is less than the previous term. No questions on that. That means 1 by 5 is greater than 1 by 6, which is greater than 1 by 7, which is greater than 1 by 8. No? So, all the first 3 terms are less than 1 by 8. Correct? That means, if I replace the first 3 by 1 by 8, plus 1 by 8, plus 1 by 8, and last one, of course, I leave it as 1 by 8. Supposing I do this, what is the total I will get? I will definitely get a lesser total. Therefore, this summation of the, you want to call this Sn, whatever, will be definitely less than the second series that I am going to write, correct now? Because each term, most of the terms are lesser. So, total also will be less. So, this total is less than 1 plus half plus 1/4 plus 1/4, of course. Here I am adding 2 terms now. So, first I will add 2 terms, replace them with the least of those, then take the next 4 terms, replace each of them with the least of those. Next take 8 terms, replace each of them with the least of those. So, you will have how many 1 by 16s? 8 number of 1 by 16s and so on, right? So, now what is this equal to? 1 plus half plus, what is 1 by 4 plus 1 by 4? Half plus, what is 1 by 8 plus 1 by 8 plus 1 by 8 plus 1 by 8? Half. What is 1 by 16 plus 1 by 16? 8 times. You have to add half. Plus 1 by 32 added 16 times will be half. 1 by 64 added 32 times is half. Plus half plus half plus half plus half. Correct? No? So, therefore, this is going to infinity. And our friend is actually less than this. Or rather, I should say greater than this. I wrote less than, I should have written greater than. Our Sn is greater than this number. This, when I write smaller values itself is going to infinity. So Sn definitely is divergent. Oresme gave this proof. Like I said, in the 14th century, but nobody remembers his name, right? Or we do remember. 300 years later, our friend Cauchy came. He gave a generalized version of the same way of combining, grouping the items. It's called the condensation method. This is known as condensation method of Cauchy. It is actually called Cauchy's condensation method with no mention of our friend Oresme. Anyway, Oserme, I think it's Oresme. Anyway, I must have written that wrongly. Doesn't matter. So that is a divergent series, right? So now we go back to our exponential series that we had, and we can start discussing. First thing that we want to do is to find out whether it is convergent. I think that's what we need to do. And that is the method used is approximately similar, like we replace that series by another series whose property we already know. No? So that means actually what method that is usually employed is as follows. Supposing I got two series, infinite series. So I got one A0 plus A1 plus A2 plus etc. is one series. I got another series which is B0 plus B1 plus B2 plus etc. Now we also can prove a condition that AN is always less than or equal to Bn. Let's assume that is the case. That means every term of A series is either equal to the corresponding term of B series or less than the corresponding term of B series. Now, if you find the B series is convergent, obviously A series must be convergent. And if you find A series is divergent, B series must be divergent. Correct? No? That is the conclusion that we have drawn. That means we have to generate a new series. Term by term, we should have this property of between the two series. And based on the convergence of the other series, we can decide on the convergence of our series, right? So now that we'll take up that to prove the convergence of this fx. Now this fx, we are saying an individual term. If you look at if you write that as a partial sum, the last term or one term is x power n by n factorial. We have seen that n factorial is always increasing and always tame any other large number. We know that eventually this goes to 0. That we know that once n crosses x, see till n is, x is any number, yeah? X can be 100, 2, 4, whatever, no? So till n is less than x, these terms are increasing actually, right? We'll rewrite that to show that. I'll rewrite this fx in a slightly different way. Fx equal to 1 plus x by 1, no problem, plus this x square by 2 factorial, right, as the previous value, which is x by 1, multiplied by x by 2, right? And the next, which is x cube by 3 factorial, I write as x by 1 multiplied by x by 2 multiplied by x by 3 plus etc. Correct? So now I will reach a place where I'll get a term which is having x by 1 into x by 2 multiplied by so on, multiplied by x by some n, capital N, n term, where this capital N is bigger than x. If the capital N becomes bigger, it is going to eventually become bigger than anything. No? So once n crosses x, the successive terms beyond this will start reducing, correct? And they go to 0. So our fundamental test is satisfied. Individual term is going to 0, that is fine, no problem. But we have these initial numbers, quantities, which may be bigger than 0, maybe a big number also, we don't know actually. For testing convergence, I don't want to worry about these quantities. I want to only look at the point beyond which it starts decreasing. Up till here, actually the sum is increasing, right? I would like to look at that. Yeah, so like I said, I want to only worry about the terms once it starts reducing. So let us do one thing. We'll rewrite this fx as some previous total. I'll just call it px. Plus, beyond which we start getting the terms which are lesser and lesser at each place, right? So, and that will be at some value, I can call it n by n factorial plus x power n plus 1 by n plus 1 factorial n has already crossed x here, so that means each time you are multiplying by x by n, which is less than 1. Now you know it already satisfies our ratio test, if you want to call it a test, that the successive terms are now monotonically decreasing, right? So that's why I separated out the part where it is actually increasing, which is a finite number. You can just keep that number aside and we only look at the part where it starts increasing. Now we know that a geometric progression with a ratio less than 1 always converges, right? So what we can do is we can even start with a place where, I would like to start with a place where x by n is less than half. Can I do that? I just have to double this n here. Just increase beyond this x. That means you can see n is greater than 2x. N is an integer which is greater than 2x. If you have that, then x by n will be less than half, right? Let us reach a point. Up till that we total it up and put in px. Beyond this point, each ratio that we multiply is definitely less than half. Correct? So now we compare with another series. We can call it gx, which are the same old px, we don't change that, plus x power n by n factorial, plus, now we don't multiply this by x by n plus 1. We are supposed to multiply this by x by n plus 1 to get the x power n plus 1 by n plus 1 factorial. Now x by n plus 1 is less than half, right? But I will multiply by half only. Which means I will say x power n by n factorial multiplied by only half. It's actually less than half. I am multiplying by a bigger number. Actually I am multiplying by a bigger number. This is less than half, no? That x by n is less than half. Plus x power n by n factorial multiplied by half squared. Plus etc. Correct? So now each multiplication I am doing for these terms is is more than what is here. Correct now? What is x power n plus 1 by n plus 1 factorial? Yeah? You don't, I'll write that separately and show you. This was x power n by n factorial multiplied by x by n plus 1. Correct? So we are multiplying this x power n by n factorial by x by n plus 1, which happens to be less than half. Now I am multiplying by half, which is actually a bigger number. Half is bigger than that, x by n plus 1. Next time again when we multiply by half, that half is bigger than x by n plus 2. So every time we are multiplying by a number which is actually bigger. Therefore the terms of this gx, if you see, are actually bigger than the terms of fx. Correct? So I could have written that as a less than or equal to. Instead of saying gx equal to, I could have said fx is less than or equal to px plus the series. Correct? Now this part you can see is a geometric series. So you can write that equal to, this you can actually calculate now. Px plus x power n by n factorial is a common factor for all these terms. 1 plus half plus 1/4. It's a beautiful geometric series and we know it converges to 2. Correct? 1 plus half plus 1/4 plus 1/8 etc. converges to, it's definitely a convergent series and we know what it converges to also. So equal to px plus x power n by n factorial multiplied by 2. Correct? Now this total is a known final quantity and we have just proved that our fx, original fx, must be less than or equal. Actually must be less than, there is no equal to also. It's definitely less than this finite quantity. Therefore, that exponential series is convergent. Absolutely no doubts about that. Whatever value x you start with, doesn't matter. Terms seem to keep increasing in the beginning. Later they will start reducing it and go to 0 and the total always has a limit. That's what we call fx. That is the function fx is the limit of that final limit, which is a convergent value, is a convergent limit. So we have compared the two series For comparing that, and in fact generating that is what we are applying this test, you know. This is like an examination, yeah. Let me just talk of that examination or test. How do people conduct examinations? It's very important. Now this is a test we conducted. The first test, actually we conducted 2 or 3 tests on this, 2 tests. First test was the individual term has to go to 0, that's the minimum test anyway. Without that there is no question of checking for anything else. Next we conduct the next test. Can it be compared with a geometric series which converges? No, that is the test that we are doing, right? So that so we are doing one more test. So given any infinite series, we need to be able to conduct a test. It may not be always possible to get a nice geometric series like this for this thing. No? So that means people come up with different kinds of tests on infinite series to find out whether they are convergent. No? So now the discussion now is that test a good test or a bad test is the question. You understand? Now one of the tests our initial test itself is not necessarily a good test. No, I'm saying we already seen that an individual term going to 0 does not necessarily prove that the series is convergent. Harmonic series was divergent. So that test actually failed. You understand? So that means when you take a test or give it, actually not take, actually you should say give a test to a set of infinite series as a candidate. I can give a test to 10 infinite series or 100 infinite series and so on. No? So what I am really discussing right now is the effectiveness of the test. Is that a good test or a bad test? Okay, that's what I am actually looking at now. Now, how do we decide that? How is that a good test or a bad test? No? So I look at our regular exams or tests people do conduct, and I can recall one test or one set of exams as one test which I appeared in about 52 years back. So that is the IIT entrance test. That is also a test. What are the purpose of IIT entrance test? If you look at IIT, what do you call it? Joint entrance exam. No? G. IIT entrance. Now, IIT is a place where n number of people are supposed to study engineering, right? Now, who are the aspirants? That is the number of series who are aspiring. Like IIT is a place you got convergent fellows. No, so I want only convergent fellows. IIT says I want only. That means the requirement for those people also, there is some minimum. What I don't know what you call it. You can't call it IQ. I just call it skill level. No? So they require a minimum skill level of a student before they admit. So now they have to test that skill level. That is the exam. Now they are conducting. So they test that, checking for each of the candidates, aspiring candidates have to take the test, and the examiner will actually evaluate whether they have got the skill level. So they have to do that, and only those who have evaluated and passed, they are taken in as IIT students, right? So if you look at the students, I got students, and what do they score in the test? So I got 100% is the maximum score you can score, right? 0% is 1. I don't know if somebody scores a 0% in the test, definitely is not going to be admitted to IIT, right? So, and what is the pass percentage? Also is a question. No? Different exams have different pass percentages. In our university, I think it is 50%. IIT people may think, no, 50 is not enough. It has to be 80 or 90 or whatever. You understand? In fact, some of these tutorial institutions, before they take you in, you have to pay money for the tutorials, of course. But on top of that, it's not just enough that I'll pay money. No, sorry, boss. I also want to make sure that when you come and sit in that chair, you are depriving somebody else of that chair who also wants. there are more people who want to attend than the number of chairs available. So I don't want unworthy people to come and sit there. So they've got a skill level test there also. They'll say in SLC or PUC or whatever, you must have scored 92%, otherwise don't even come here. So they already fixed that 90% as the minimum score level, right? So IIT also would have fixed some level there saying, below this level, I don't admit students. No? So now they give that test. No? In my case, what happened, when I gave, we had one set of examinations for physics, chemistry, mathematics and English. 4 exams on 2 consecutive days. Remember, giving this exam, that's why I said give a test, no? It is expensive. Somebody has to administer that, no? That means that you need to have a huge hall where and you have to admit only those people who have their hall ticket, and there must be an invigilator there who's watching what you are doing, and then in the end they have to collect your answer papers, and somebody has to evaluate those answer papers and grade them and give marks to each one of the questions, each one of the answers, total the answer, all the marks, and then decide whether true or see. Now if it is some 100 students, they say I will conduct. In our case, we had about 1 lakh people or something like that is the number. Probably even not even 1 lakh, probably it was less. Number of people who attended, that is, who were aspiring to go to IIT. So they could conduct these 2 days exams, and already they were very tired, saying, my goodness, 1 lakh people. But today, what is the situation? In Karnataka state, you will find about 1 million people who want to go to IIT. I don't know. Correct? No? You understand? All over India, how many people want to attend, want to take that exam, runs into millions, right? So many millions. And the same type of exam that we had, if they have to conduct, is almost impossible to administer that test to so many people. And evaluation, it takes effort, it takes money, it takes effort. So many invigilators are required, so many people to evaluate, evaluate the papers, you require so many people for so many answer papers. So it's not possible to do. So how do we solve this problem? How do they solve this problem becomes the question. So what they do is, after all, when they gave a test to us in 1971, if I recall, out of let us assume that 100 people wrote the exam. It's not 100, just as a ratio. Let us assume 100 people wrote the exam. We found that a few of them, maybe 10% of them, didn't even score above 10%. And in fact, only about 5% of the students scored beyond the pass grade. And majority of them in between. Now, in this case, in between also, you can say this is the pass grade, what we call pass grade. And above this is pass, below this is fail. But now the fail also I want to categorize as miserable failure, this is, and failure. And the rest are all nice failure. The problem with this test was that this test was a difficult test. It was difficult. That means when you say whether easy or difficult, the person who scores 99 will always score above 90. Even for a difficult test, he is going to score 90, no problem. But the catch is not with these people who score above the pass level for a difficult test also. The problem will be with the few candidates in the border. These are the interesting candidates. These fellows, they're almost there, no? Just missed it. Just because the exam was so difficult, they could not cross that pass line. In my opinion, probably at least some of them were suitable to have studied at IIT Madras because the test was so difficult. And one of the professors in IIT, I still remember, for our previous batch, he did that experiment to find out whether the entrance exam they gave was very difficult, make it simpler or not. The question that they wanted to answer, because they knew that tomorrow this kind of situation will come when you will have millions and millions of people to test. So they need to look at the effectiveness of a test also. So what he did was something very simple. He said, I know for sure that these tests were difficult. How do you prove it? So we have the whole bunch, and the physics paper, first first semester they had one physics exam in the end. He gave one question paper, and at the end of that, almost everybody scored a 0 in that question paper. And the boys and girls, I should say, probably there was one girl there in the class anyway. The boys and girls, they complained, obviously saying, you can't give this question paper where everybody scores. I mean, at least somebody should score 50, somebody should score 70, somebody should score 80, right? If everybody scores a 0, what is the meaning of the test? The test has no meaning, right? They went and told him. Then he laughed, actually. He laughed, saying, boss, wait a minute, I will give you another paper. This paper was a physics examination, and which are the same questions which I gave you yesterday, where you all scored zeros, and this is the paper in your entrance exam. Actually, you have written the answers to these and passed. No new questions, same questions repeated. Identical paper he gave as an examination paper, which proved 2-3 things in this. He said, one is, people when they want to prepare for this giant entrance exam, they spend 18 hours per day studying and by-hearting and whatnot. No? So they do that and they go fully prepared. Once you get into IIT, now you say, now you are a top boss. No? So we take it easy and watch some movies. Now you can watch movies on a mobile also. Earlier we had to go on a cycle and watch. No? So do that. No? So they take it easy. At the end of the year, now you said the same answer you wrote exactly 1 year back, you had answered this and you had scored 90%. Now you are scoring 0%. That means your behavior in IIT is not so good. Maybe some of these people who just missed, these are called just missed fellows. No? You understand? It's like the husband and wife. They wanted to go to Mysore. Mysore is a simple example. To Mysore, every half an hour there is a bus. Not today, I think there is a strike. Correct. Every half an hour or every 1 hour there is a bus. Let us assume every 1 hour there is a bus. So this fellow says, I have to catch the 3 o'clock bus or 3 o'clock bus. So he is hurrying up his wife saying, get dressed fast. Come on. No. So went and reached the bus station. They reached at 3 hour 3.05. So they reached 5 minutes late. He said, I told you to speed up your whatever you are doing. No? So to get ready, you have to get ready faster and faster. Now you see, now we have to wait for 55 minutes now for the next bus. Then you know what she said? He said, I told you last time, don't hurry me so much. If you had not hurried me, we wouldn't have had to wait for 55 minutes. No, we would have to wait for less time. So, you understand? See, these just missed fellows, some of those just missed fellows who missed the IIT, probably they were better candidates than the fellows who actually got selected. They might have scored better. So you always have to worry about these. We only want to make sure that the miserable failure fellows don't get in. That is the objective, is to get as many people into miserable failure as possible, as few people into just miss type of fellows. And of course, finally, pass has to be a pass. That there is no question at all. And how to administer this exam for millions of people is, we don't do one test. It is not possible to do one test, however difficult or easy or whatever you decide. You'll always have a problem with more people falling below or more people falling above, and that problem will be there. So they do it in 2 levels. One, they give a easy test, easy to administer, easy to answer, almost easy to answer, right? Even that, these miserable failures people anyway will not be able to answer, right? So that easy test. So we have one easy test, which is what you call level 1. I don't know what they call it. In which probably 50-60% of the students will be taken down as miserable failure, right? Understand? Majority of people are gone anyway. So the rest of people, less number of people are there. Now you give that difficult test as the exam level 2. So giving a test to a series also, you have to decide, is this test very difficult for an infinite series to pass? And in fact, many of these tests have 3 possible results. If you look at infinite series tests people have designed, I am looking at the history of mathematics, there are many tests which people have given. They result in either pass, of course, which is convergent, which is nice. That's what we are looking for. Or they can also result in divergent. That is a miserable failure case. But then, unfortunately, they also have an in-between fellow, which is maybe, we don't know, maybe cases. These are the borderline cases. So that test is not conclusive. We cannot say, is it convergent, not convergent, we can't say. Now, we want to have a test in such a way that we get minimum number of series in the maybe cases, maximum number of series in both convergent as well as divergent. We want to fail, no problem. So that is not an issue at all. And that is the level of tests that we have to conduct, right? So first is that Cauchy's ratio test. That's what we are, in fact, we use that for proving the infinite series of our series convergence. We use the Cauchy's ratio test. And people found that this ratio test, that is comparing the infinite series with a geometric series, is actually a difficult test, a very difficult test. Half the time it gives maybe result. It doesn't say convergent, doesn't say divergent, or sometimes it is even difficult to administer the test. Test administration itself becomes difficult, and people are looking for easier tests in terms of to apply to infinite series and so on. Now you know the background. I don't know what sort of tests are going to be discussed as part of your mathematics education in colleges. Whatever it is, now you are prepared for it, saying, when you say, I've got a new test, you can design a test on your own and say, please apply this test to infinite series in this particular way. And you can also qualify that by saying it is difficult or relatively difficult or whatever it is, so people know what they are looking for. So they design different kinds of tests. It's not just one universal test. It's not just one test that we are talking about. So now let us come back. We have proved that this series sigma n equal to 0 x power n divided by n factorial is convergent. We have proved that. And now what do we do about this function fx? We called it exponential also. So what do we do about that? I wrote a couple of interesting results for this. One was f0 itself was 1, no question. f1 was a nice infinite series, and people wanted to give a homage to the series actually. 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, series of this, and that limit is actually called E, and value is something like 2.7182848 whatever. No? Obviously it's infinite number of decimal digits. It's an irrational, it's a transcendental number actually. So that was given the name E, because that happens to be the first letter of our friend Leonhard Euler. He did pioneering work on these infinite series. You will probably find Euler's test also somewhere down the road there to test infinite series, whether to find out whether they are convergent, and that is known as E, correct? Now we also found some interesting results earlier. One was fx multiplied by fy is f of x plus y, correct? No? Now I'll write that in a reverse order. So that means we have an E which is actually f of 1, correct? No? F of 1. What is E squared? Is E multiplied by E, which is f1 multiplied by f1, which is f2. E squared is f2. That we already proved. Fx multiplied by fy is equal to fy x plus y. f1 multiplied by f1 must be equal to f2. f2 is 1 plus 2 by 1 factorial plus 2 square by 2 factorial by 2 cube by 3 factorial, etc. X is 2. Similarly, e power n. What is e power n? Is f of n. Correct? You understand? Just by multiplying. You multiply once again by e squared multiplied by e will be f of 3. So what is e power n? is Fn. So now for any natural integers, we find Fn, now we read it the other way around. What is Fn is actually e power n. I derived it as e power n equal to Fn, but actually Fn is e power n. Therefore, we'll assume that e power x is equal to that series, fx. That means we are assuming this is a integer, of course, the way we have shown. But this multiplication we have found is true for any real number. Now x and y need not be integers. That means n need not be an integer at all. N can be any real value. That's what I am writing. So e power x is any real number, must be equal to x by 1 factorial plus x square by 2 factorial plus 3. That is e power x, where e is this. It is also known as the base for natural logarithms that we can see at a later date. Okay, so e power x is this. This is what is known as the exponential series, right?